Welcome to another video, the fourth video in higher order thinking. Today I got a really cool pseudoprime test. It's I haven't seen it around many places, so I figured I'd share. What we're going to be talking about is we're going to be doing a pseudoprime test using decimal expansions of a number. Kind of weird, huh? Well, here goes. We gotta learn. You gotta know a few facts that you probably already know. Is this Euler's function, and a special case of it when n is prime, it's the Fermat-Little theorem or function. Those are going to be a key role, play a key role in this new pseudoprime test. So if you don't know about these, check them out, read up on them. But they're pretty common. So this Euler's function, a and n both have to be relatively prime. That's the key fact. This doesn't work if they're not relatively prime. This formula doesn't hold. The special case of Fermat's-Little theorem that always holds, because if n is prime, then Euler's formula reduces down to p minus 1, and it'll always hold if a and p are relatively prime, and that'll happen if a is not a multiple of p. So it's okay. So let's see how this is going to happen. Decimal expansions. We can write the number as this 0 point first digit being a1, second digit being a2, and so forth. And then you reach a point where b1, b2, b3 up to bt is the repeat of the decimal expansion. Remember, a fraction will either repeat or won't repeat at all. So the repeat is the key element of this. And say we do this trick. We multiply by this 10 to the s plus 1 minus 10 to the s power thing times our decimal number. What we're going to get is some number y. We don't really know what that y is because it's an arbitrary number, right? So, but the important thing is it's an integer. And it's kind of like we're canceling out things to make this number into an integer, this r decimal number into an integer. Okay, so the next thing we do is let's solve for r, and we get this r equals y over this quantity, the ts plus t minus ts quantity, and that's a fraction, and we can represent this fraction as some m over n. Well, we'll assume that we've already reduced this fraction, so it's GCD of m and n are equal to 1. So they're all completely reduced. Now, since these are equal, right, this implies that this identity holds, right? Because y over 10s plus 10 to the power s plus t minus 10 to the s might not be reduced, but we said that m and n are reduced because the GCD of m and n is 1. That's what we said. So that means that n would have to divide this 10 to the s plus t power minus 10 to the s power, and that's exactly what that identity says. N may equal it if 10 to the s plus t minus 10 to the s is the smallest, is reduced. There's no common factors between that and y of it. But we don't know that yet, so we're just saying that. Now, if we check, as our algorithm is, if we just check two numbers, 2 and 5, that they don't divide into n, then we can actually reduce this further down into 10 to the t equals 1 mod n. And remember, t is the length of the actual repeating part of your decimal expansion for your number. So 10 to the t equals 1, we're looking for when that's true. Now, some facts is from the Euler function, t always has to at least divide your Euler function. Okay? So that's one fact. But the big trick to notice is that if n was prime, then t would have to equal n minus 1 by Fermat's little case. So the composite test is basically to check the repeat length of your decimal number is 1 less than the denominator length, denominator's value. So this is like a pseudoprime test. It's a composite test. It's not a full prime test where it rules out every prime. God, no. Wish it was, but it doesn't. But let's do a concrete example to show what I mean by all this. If it turns out that t was strictly less than n minus 1, I mean, and it has to divide the Euler function, but it doesn't necessarily have to be n minus 1, that would be a sure sign that this number is a composite number. It can't be a prime number. But if we arise that t equals the n minus 1, then it can be either a prime or a composite number that passed this kind of test. Like a very hard one is the Carmichael's numbers and stuff. They pass all these composite tests very well, and it's very hard to rule them out in a lot of cases. But I'm not going to get into those today and stuff. So let's see how this is done. So here's the example. Suppose we want suppose we want to determine if n is prime. Then we look at 1 over n and compute its repeat length. If it is equals n minus 1, then it might be a prime. If not, then it's definitely not a prime. It's a composite. So here's the example. A simple, stupid example, but it gets the point across. Say we want to compute if 7 is probably prime. If we compute 1 over 7, do the decimal division with your big decimal library from your arbitrary precision library packages that you use for your programming language, so you aren't restricted to like floating point sizes, so you can deal with large numbers. If you do that one computation, that one intense computation to get the decimal expansion of the number out to, a reasonable repeat length, and then you find that the length is 1 less than the denominator. In this case, 1 over 7 is equal to 0.142857. Repeat over and over again, and you can see 142857 is 6 digits, and that 6 is 1 less than 7. So you get the repeat length is 6, which equals 7 minus 1. So it could be prime. It didn't rule out compositeness. It didn't give us full primeness of the number, but it did demonstrate that this could possibly be a prime. It's not something that it's not something that we know is composite yet. So thank you for watching. I hope this was a cool, neat way of actually computing like a pseudoprime test for things. It's a creative way, and it links things that you wouldn't even think that can be linked together. Have fun, write some programs in it, see if you can compute some decimal expansions and look at the lengths of them and stuff, and see you know, see if there's any times when you get weird primes, weird large primes, um, being able to determine if they're composite, weird numbers, I should say, being able to determine if they're composite right away with this kind of trick or something. I feel like it's going to be a very computationally intense kind of algorithm, so it's not the best algorithm to use, but hey, it's the thought that counts sometimes. Thanks for watching, guys, and I hope you come back for the next videos.